Have you ever just looked around and wondered what all this stuff is really made of? I mean, if you could zoom in, way in, past what we can see, what are the actual building blocks of, well, everything? Today, we're going to do just that. We're going to find the Legos of our universe.
So, right off the bat, let's just try to get our heads around the insane scale we're talking about. Imagine an entire football stadium. That's one atom. Now, almost all of its mass, all the stuff it's made of, is packed into a nucleus the size of a single blueberry sitting on the 50-yard line. The rest? It's pretty much just empty space. Wild, right?
So, here's our game plan. First, we're going to peek inside that tiny blueberry nucleus. Then, we'll figure out how each atom gets its own unique ID card. After that, we'll look at the ultimate cheat sheet for chemists, the periodic table. And finally, we'll see how all these atomic Legos actually snap together to build the world. All right, let's dive right in. Section 1. Inside the atom. Time to start peeking inside these fundamental building blocks. Okay, so every single atom is made of just 3 key parts. Inside that nucleus, you've got your protons, which are positive, and your neutrons, which have no charge. And then, zipping around in all that empty space of the stadium are these tiny, negatively charged electrons. It's that simple. Protons positive, electrons negative, and neutrons are neutral. Now check this out. What's really wild is the mass. Look at that last column. Protons and neutrons are the heavyweights, clocking in at about 1 atomic mass unit. But the electron? Whoa, it's almost 2,000 times lighter. That's why we say the nucleus has all the mass. The electrons barely even register on the scale. So a normal, neutral atom has the same number of positive protons and negative electrons, right? It's perfectly balanced. But what happens when that balance gets thrown off? Well, it becomes an ion. It's just an atom that's either gained or lost an electron, which gives it an overall electric charge. And the key thing to remember, and this is huge, is that the number of protons never changes. That's its unchangeable identity. And there are 2 flavors of ions. If an atom loses a negative electron, it's left with more positive protons, so it becomes positively charged. That's a cation. Here's a little trick. Think of the T in the middle of cation as a little plus sign. Now, if it gains an electron, it gets an extra negative charge, and that's an anion. Okay, so if the number of protons is the core identity, how does that work exactly? Well, that takes us to Section 2, an element's ID card. Let's learn how to decode their language. This right here, this is the single most important number in chemistry, the atomic number. It is, quite simply, the number of protons in the nucleus. Any atom with 6 protons is carbon, period. Any atom with 8 protons is oxygen, no exceptions. It's the absolute defining fingerprint of an element. The second number you gotta know is the mass number. This one's easy. It's just the total count of the heavy particles, so protons plus neutrons in the nucleus. And since we already know the electrons weigh next to nothing, this number gives you a really good idea of the atom's total mass. So this is how you see it written down, kind of like a secret code. The big letter C, that's the symbol for carbon. The number up top, the superscript, that's the mass number, 12. And the number on the bottom, the subscript, is the atomic number, 6. A lot of times you won't even see that bottom number, because hey, if you know it's carbon, you already know it has 6 protons.
So, what happens if you have the same number of protons, but you mess with the number of neutrons? Then you get isotopes. They're basically different versions of the same element. They have the same identity, same chemical personality, but they have different weights because of those extra neutrons. Same element, just a little heavier or lighter.
And this isn't just some abstract science stuff, it has real-world consequences. Take the iodine it's added to table salt to keep our thyroids healthy. That's not just a plain iodine atom, it's an iodine anion, an ion. That tiny little change at the atomic level, gaining 1 electron, makes a massive difference for our health. It's pretty amazing.
So now we know how to identify all these different elements. But how do we organize them all? Well, that brings us to Section 3, the ultimate cheat sheet. We're talking about the most powerful tool in all of chemistry, the periodic table. And this thing is so much more than just a colorful chart on a classroom wall. Back in 1869, the guy who came up with it, Dmitri Mendeleev, he saw gaps in his table. And he was so confident in his pattern that he actually predicted the properties of elements that hadn't even been discovered yet. And when they were found, they matched his predictions almost perfectly. The man was a chemical prophet.
And here's the magic rule that makes the whole thing work: the periodic law. All it really means is that when you line up the elements by their atomic number, that all-important proton count, you start to see these amazing repeating patterns in how they behave. Elements in the same column? They're like family. They act in very similar ways.
The table also breaks everything down into 3 basic groups. Over on the left, you've got your metals. Think shiny, bendy, good at conducting electricity. Then up on the right, you have the nonmetals. They're usually dull and aren't great conductors. And straddling the line between them are the metalloids, which are kind of like a hybrid of both. Okay, we've got our elemental Lego bricks. We've got our instruction manual, the periodic table. So that brings us to our final section: how atoms form compounds. Let's see how we actually click these pieces together to build, well, everything. Turns out there are 2 main ways atoms get together. The first is an ionic bond. This is where one atom straight up gives an electron to another. This creates a positive and a negative ion, and just like tiny magnets, they stick together. The second way is a covalent bond. This is more of a team effort, where the atoms share electrons, locking them together into a unit called a molecule. And when we want to describe one of these molecules, we use a molecular formula. It's literally just a parts list. Take acetic acid, the stuff that makes vinegar sour. Its formula, C2H4O2, tells us each molecule is built with 2 carbon atoms, 4 hydrogen atoms, and 2 oxygen atoms. Simple as that.
But this brings up a really interesting question. If you have that exact same parts list, 2 carbons, 4 hydrogens, 2 oxygens, could you snap those Legos together in a different way and build something totally new?
And the answer is absolutely yes. And this gets us into the super cool concept of isomers. These are compounds that have the exact same formula, the same parts list, but they're built differently. So C2H4O2 can be acetic acid, or you could arrange it differently and get methylformate, which is used in insecticides. Same parts, different build, totally different result.
And get this. This is my absolute favorite example. There's a compound called carvone, and it has 2 isomers that are literal mirror images of each other. That's the only difference, but your nose can tell them apart in a second. One version smells like spearmint, its mirror image smells like caraway seeds, the stuff in rye bread. A tiny flip in the structure completely changes how we experience it. It proves that structure is absolutely everything.
It really just blows your mind, doesn't it? If the only difference between spearmint and caraway is just a mirror image arrangement of the very same atoms, it makes you wonder, what other incredible secrets about our universe are just hiding there in plain sight, waiting for us to unlock them in the language of chemistry?